Today, we're digging into a really fascinating paper from Google DeepMind, and it puts one of the most fundamental pieces of modern AI directly under the microscope. We're talking about vector embeddings, the unseen engine behind pretty much everything. But this paper asks a really sharp question. What if they have a hard mathematical limit? That's the provocative idea we're going to explore.
And yeah, this isn't just some casual thought experiment. This is a super rigorous investigation from one of the top AI labs on the planet. They are fundamentally questioning a paradigm that has dominated information retrieval for years. And what they found, well, it could change how we think about building these systems from the ground up. So here's our roadmap for today. We're going to start with the big picture. Why embeddings are such a huge deal. Then we'll dive right into that core question of a fundamental limit, get into the deep math behind it, see how they tested it, and then watch them break state-of-the-art models with a custom-built benchmark. Finally, we'll look at what all this means for the future.
First up, the embedding revolution. Seriously, if you've ever used a search engine, gotten a product recommendation, or talked to a big AI model, you've been using vector embeddings. They are this powerful, invisible force that's constantly making sense of our digital world.
The basic idea is actually kind of beautiful in its simplicity. You take something really messy and unstructured, like a paragraph of text or an image, and you map it to a single point in this giant geometric space. It's just a list of numbers. And the whole idea is that the closer 2 points are in this space, the more similar their original content is. Simple, elegant, and, as it turns out, incredibly powerful.
And this quote from the paper just perfectly nails the problem. We've gotten so good at this, and we rely on it so much, that we're basically asking this one technique to do everything. Simple search, complex reasoning, following instructions, writing code, you name it. We're just assuming that a single vector can somehow represent any possible query and any idea of what's relevant. But can it, really?
Which, brings us right to the core conflict here. The sort of prevailing wisdom in AI for a long time has been, just scale it up. You want a better model? Just add more data, make the model bigger, use more dimensions, and you can solve anything. Well, this paper challenges that assumption head-on.
This right here is the question that drives the entire paper. It's not about whether our current models are good enough. It's about whether it's even possible for any single vector model, no matter how huge we build it, to represent all the complicated relationships we need it to.
So, just so we're all on the same page, the specific thing we're talking about is called dense retrieval. It's simple. You embed your query into one vector, you embed every single document in your database into its own vector, and then you just find the documents whose vectors are closest to your query's vector. That's the entire game.
All right, now we're getting into the real theoretical heart of this thing. The researchers connected this problem to a whole other field called communication complexity theory. This is an area of math that deals with, how much information two people need to exchange to solve a problem, which is a perfect analogy for a query in a document, right? Let's see how they use this to build their case.
The key mathematical tool they use is this thing called signrank. Now, forget the exact values for a second. Signrank just asks a much simpler question. What's the absolute minimum number of dimensions you would need to create a matrix of scores that just gets the signs correct, positive or negative, compared to some target matrix? It's basically a measure of how complex a relationship is to represent.
And here it is, the core mathematical result. So let's say A is our perfect ideal relevance matrix, just a giant table of ones and zeros, where rows are all our possible queries and columns are all our documents. The term on the right, rank NTROPA, that represents the absolute rock-bottom minimum embedding dimension you'd need to perfectly capture everything in matrix A. And this inequality proves that this minimum dimension is always bigger than or equal to the sign rank of that relevance matrix. In short, the complexity of the problem itself puts a hard floor on how many dimensions you need.
So what's the bottom line here? It's actually pretty profound. Since you can construct matrices with an arbitrarily high sign rank, it means that for any embedding dimension D you pick, I don't care if it's 1024, 4096, or a million, there will always be some retrieval problem, some relevance matrix A that is mathematically impossible to solve perfectly. You just don't have enough dimensions to capture all that complexity.
Okay, that is a really powerful theoretical claim. But, does it actually hold up in a real optimization setting? To find out, the researchers designed this brilliant best-case scenario experiment they called free embedding optimization.
So in this setup, they just threw out all the messy natural language. They just created raw vectors for queries and documents, and then used gradient descent to directly optimize them to satisfy all the relationships they wanted. And what they found is exactly what this chart shows. For every dimension D, there's a critical point N, a certain number of documents, where the whole system just breaks. It literally cannot represent all the possible top two combinations anymore. Sure, if you increase D, you can handle a larger N, but that breaking point, it's always there.
And here's where it gets a little scary. By plotting these critical points, they found the relationship fits a third-degree polynomial almost perfectly. And when you extrapolate that curve out, well, the results are pretty stark. Even a massive 4,096 dimensional embedding, in this perfect ideal scenario, hits its representational limit at around 250 million documents. Now that sounds like a lot, but believe me, that is a tiny, tiny fraction of the web.
So theory and these ideal experiments are one thing, but what about the real world, with real models? This is where the paper gets really fun. They created a custom dataset called Limit, specifically designed to be a real-world test of this theoretical breaking point.
On the surface, the task looks like a piece of cake. The queries are just who likes X, and the documents are just these short profiles like John likes quokkas and apples. But the trick is all in the setup. They basically created a relevance matrix that forced the model to be able to represent every single possible pairing between a group of 46 people. This creates this worst-case scenario, a matrix with a super high sign rank, which is an absolute nightmare for a single vector model.
And the results? Whoa. It was a bloodbath. They tested the best publicly available embedding models, GRIT-LM, Gemini, QN, and they all just completely fell apart. Most of them struggled to get even 20% recall after retrieving 100 documents. But you see that clear trend. Models with higher embedding dimensions did a little better, but none of them even came close to solving it. The theory holds up.
And just in case you were thinking, well, okay, maybe it's just a needle in a haystack problem in a big database. Nope, they created a small version with only the 46 relevant documents. That's it. And even here, with the answers right in front of them, the best models still can't get it right. They struggle to even hit 60% recall when they just need to find the top 2 documents. It's not about finding the documents. It's that the models fundamentally cannot represent the relationships required to rank them correctly.
Okay, so if the single vector paradigm has this fundamental mathematical limitation, where do we go from here? This is what the paper explores in its conclusion, kind of looking around the corner at what the future of information retrieval might look like.
And what's really telling is looking at what did work on this crazy hard limit task. On one side, all the single vector models fail. But what's fascinating is that an old school model like BM25, which just matches keywords, does great. And multi-vector models like Colbert, which represent documents with a whole bunch of vectors instead of just one, also do much, much better. They succeed for one simple reason. They escape the single vector bottleneck.
So there are a few paths forward, and they all have their own trade-offs. You've got cross-encoders, which look at a query and a document at the same time. They're super accurate. One of them solved limit perfectly, but they're way too slow for searching through billions of documents. Then you have multi-vector and sparse models. They're more expressive, they're faster, but it's still kind of an open question how well they'll handle the really complex reasoning and instruction following we want AI to do.
And that really brings us to our final, lingering, and honestly pretty unsettling question. Vector embeddings have been wildly successful, but this research reveals a potential crack deep in the foundation. As we keep asking our AI systems to understand more and more complex relationships, are we pushing this single vector idea past a fundamental breaking point that no amount of scale can ever fix? It's a critical question for the future of this whole field.